So I'm Rolf Hutt, and I'm going to present eWaterCycle, a project that I worked on in the last year and a half, 2 years, I guess. And that is a collaborative project with Dr. Niels Drost from the eScience Center, which is a center that provides computational high-performance computing expertise to scientists in the Netherlands. It's part of our funding agency structure. So you can actually do calls to them. Edwin Satunadiaya from Utrecht University, who is an expert in hydrology and global models. And the PIs are Niels van der Giezen. That should be Nick van der Giezen and Mark Bierkens. I have to admit, I'm not a computer scientist. I'm a water management hydrologist. But what we realized at some point is that in the world, it's kind of everybody expects this to be available. You just go on the news and you just watch the news and people tell you what the weather's going to be over 5 days, 10 days if you're lucky. And if you work in earth sciences for a while, then you know what's needed to make sure that everybody has that. Because it's not trivial. To have that weather forecast, what we do is we need observations of meteorological phenomena. We need a very good understanding of the physics that are going on. We need some kind of numerical model that takes these physics and can on a given day forward calculate what was going to happen. And you need some brick and mortar. You need some place where an actual computer is doing that. Nowadays people would draw a picture of the cloud here, but that's not fair. Most of the weather predictions are still done by institutes that own their own large supercomputers. And being from a group that does hydrology and water management, we thought, why do we have a weather forecast globally available everywhere, but why don't we have a forecast of flooding globally available everywhere? Basically what we want to do is provide the world with a global available high resolution river discharge forecast 9 days ahead. And then to provide the link with the energy sector, if you have river discharge available, one of the biggest uncertainties in reservoir management is how much is my inflow going to be. So all management decisions for hydropower rely on very good estimates of inflow, both on the short and the medium scale. And we think that we know from working together with a lot of hydropower operators that their short scale predictions in a lot of areas, not all of them, the Germans are pretty good, but in a lot of areas in the world, the short-term predictions of inflow is just not good. And if you have a global model, you can suddenly provide way better management options. Maybe less trivial, but in the Netherlands we sometimes have power issues because the river levels are too low and the temperature of our rivers become too high, so they can't be used for cooling water. So also the link with energy is also in if we have good predictions of river discharge and couple that to a nice river temperature model, we could predict when a power plant needs to shut down because it can't cool anymore. Usually this is, by the way, an environmental concern, not necessarily a physical or economic concern. These power plants are not allowed to extract too much or dump too much warm water back. I took a picture of cooling towers with EVAP, but a lot of the times they just take in cold river water and dump in warm river water back into the river. And they have a regulation on how much warm water they can put into to not offset the ecosystem. Also, if energy companies have better predictions of river discharge coming in, they could have more efficient management strategies, basically. So going back to the equivalent of meteorology versus the water world, what do we have? Well, in the water world, we do have pretty good observations. We got satellite observations of soil moisture. We do have a good understanding of how water moves through the earth and over the earth and in rivers, so that's all available. We do have numerical implementations in code of these physics, but what we don't have are those bricks and mortars. And we don't have an integration that puts it all together, and that is what eWaterCycle aims for. We really hope, of course, once eWaterCycle moves from being an academic project, that at some point, we're in Brussels, we're talking funding, someone sets up an institute with the actual brick and mortar that's going to run this for the entire world. I'll get back to that later. Talking about these models that calculate river discharge globally, the models that are now available and that are globally, I know there's some people that run very high resolution models, but they're usually run locally. So the only global models that are available are usually used for climate change analysis, and they are pretty coarse. Basically 1 degree, sometimes half a degree, if you're lucky, quarter degree global models. And everybody knows if you want to do operational forecast, that's not the scale at what the water system needs information at. So what we want to do, and I have to thank Google in one of their April Fool's Day jokes for providing this map, we want to basically take this kind of resolution and prove that you can also run it on this resolution. This is from our visualization that I will come to in a few moments. The way we want to do that is we don't want to reinvent the wheel, because we believe that everything needed to do this is already available in different components. So we want to use what is available. We will have to improve what needs improving. Sometimes we need to build new things to make this happen. And since we're a very strong believer of open science, we're going to share everything that we've made so that other people can use it and build on it. Practically, this means that we've limited ourselves to using open source existing components. So we didn't use proprietary code at any point, and we didn't use stuff that wasn't published yet but was still in an academic setting. You have a lot of hidden academic code in the papers if you start looking for it. We would build on that by branching, forking, and adding to repos of people that did that. And to make sure that everything was interconnectable but also interchangeable, we made sure we used open interfaces between all the different components of our eWaterCycle system. So what does that look like? What we do is we have a global model. We're using PCR Glob, model developed in Utrecht. We're running 25 ensemble members of that. We're forcing that with the GFS data from the Americans. Somewhere this summer, we hope to switch to the higher resolution data that's available from ECMWF. So every time a new weather forecast becomes available, we run our model. But the starting point, we do data simulation based on satellite observations from soil moisture. The result of that is then put to a NCWMS server and into a nice visualization. These components all existed. It was just that nobody had put them together to run an operational model. The interfaces I talked about, we use industry standards here. So we're using NetCDF as input formats, NetCDF as output format to the visualization and to the archive, WMS for the visualization, and BMI, the very inappropriate acronym, because if you Google for it, you get all kinds of health tips instead of just a basic model interface that it's supposed to be. So people that come up with acronyms first Google what you thought up and then decide if it's a good acronym. But the basic model interface is, in its implementation, very useful to couple models with each other, model components with each other, and also data simulation schemes, in this case, to a model component, to a model. Okay, what does that then look like? I'll go to my, So this is the blurb that we always put up there that basically says, this is very much in beta. The model that we used was not calibrated for the use we're doing. The model was calibrated for reanalysis and global runs for climate change. And we're using it on a way higher resolution than it was intended for, and we're using it for operational runs with a different input. So please don't evacuate your country based on what we're predicting. So this is, at this moment, we're looking at the predicted dish. So we're lagging a few days behind. We're running this on the Cartesia supercomputer in Amsterdam. It's a research computer. It has job scheduling, and saving people from drowning, especially in a beta version, is not important enough compared to astronomy. So yeah, someone is now probably calculating something else. And when we get our computer time back, we're going to catch up. I think we need about 3 hours wall time for 1 day prediction, approximately, on 3 nodes of Cartesia. So it's not that heavy. It's just mainly memory heavy. This is the discharge predicted in the Irrawaddy, very close to the confluence with Chindwin. But you can pick any pixel you like. So this is one of the for little streams that feeds into that. About 600 cubes per second. And and so if I do low bit, which of course for my country, the Netherlands, is an important point. This is nowhere as good as the Dutch Rijkswaterstaat can predict. So there's a lot of places in the world where local authorities have on a local level a better system. We're aware of that. I'll come to that later at a later moment. But if we, whoa! Yeah, that's the cesium. So the stars in the background are actually accurate. So that's something you get for free if you just implement this on cesium. But if you go to little side streams in Nairobi area about, let me see, Lake Victoria. I'll take this one for example. Nobody is predicting what's happening here yet. And we are. So in a week or something, we're expecting double the amount of flow in this little river. Again, please do not evacuate your country based on this data. But I think it's important to show that we can do that. And that was the main point of even constructing this system. We wanted to show that using existing components, I think we wrote less than 1,000 lines of code to get it all together. You can build this. So it's not that the science is not out there. This is actually doable. I want to come back to that part. So this is very close to, this was when we just started it up, first few weeks, we started looking at this and we thought this probably, look, it goes from 200 to 1400 cubes per second in a very small, so we thought that this is probably still some errors in our model. This is unlikely, and 1 week later, this was in the news. This is, if I'm going to look, I'm probably going to find a lot of false positives. This was an actually positive, but it shows what the impact can be. Because for countries like this, the current lead time is 1 to 3 days. And we hope to be able to extend that at least to the length of the weather forecast, so 9 days, hopefully even longer. Since this is a symposium on high-performance computing, I want to focus on some of the issues we've been having that we think are particulate to our domain, water and water management and hydrology. In the data simulation scheme, every ensemble member takes up about 10 gig of memory. And the observations are about 1 gig of memory. and we're now running at a 10-kilometer pixel size. To provide forecasts at relevant scales, we need to go to 1 kilometer, maybe at some point 100 meter. You can then calculate how much memory we need. It's not CPU intensive. Hydrology in itself doesn't have a lot of difficult equations to solve, and it doesn't need a lot of iterations to solve them properly. But in comparison with meteorology, in meteorology you just get your laws of physics, but your constants and your parameters are the same everywhere. Whereas in hydrology, you get your laws of how water move, but your soil type is different everywhere. The way it moves, the conductivity of the soil, or the type of plants you have that all changes, and that dramatically increases the amount of memory needed for a single run. So our biggest problem is I/O, especially in the data observation. You get new data in, you need to have a new starting point based on the new data, you need to get a new estimate, where there's a huge matrix inversion if you're doing a classic ensemble Kalman filter, which will implode at some point. We need to come up with smart ways to do that. That is one of the challenges for the HPC community to be solved, to be able to help us run this at higher scales and further time lengths. One of the things that I'm working on together with one of my PhDs is coming up with smarter ways to do ensemble Kalman filtering, where you don't need the entire inversion of the entire state matrix, but can come up with something smarter that requires less memory, even if it comes at the cost of more CPU. Because again, in our particular case, that's not the bottleneck. In summary, what's in our system right now? We're running the PCR Glob WB, it's a very nice acronym, model 2.0. We couple that with BMI. And something that I also want to mention for this crowd, we're using Thrift. Who's familiar with Thrift? Thrift is a object translation service once developed by Facebook, but it's kind of a client-server system where you can talk Python on one side, Java on the other side, and so I can have a Python model and a Java data simulation scheme, and the data simulation scheme will just talk to the model, and it won't even notice that the model is written in Python. And the other way around, the Python model will talk to the job control or whatever, and it won't even notice in what language it's written. That was developed by Facebook for integrating their track everything you want schemes, I guess. Well, database versus front end versus, well, you get all that. And we took that and we used it to have OpenEA communicate with the model. And we made a version of BMI Thrift, basically. In the future, yeah, I'll tell that now. I just said that Germany, for example, has a better model than we do. It's locally, it's calibrated, it's whatnot. In the future, we're applying for funding. The proposal should be on a desk within a few kilometers here. What we want to do is we want to be able to say, these 5 pixels, I don't want to run PCR Glob on these 5 pixels, because I just had a PhD that spent 4 years on getting a better model for these 5 pixels because they're my backyard. This happens a lot in hydrology, where people go measure and come up with a new model that is like the best model for their little catchment. If you have that, I want you to be able to provide that to eWaterCycle, and we can just say, we're going to run your 5 pixels in our model. And I don't care if you've written them in Fortran, because if you implement Fortran BMI, then we can just talk to Thrift with you, no problem. And that would help us to get the best model locally, everywhere, connected into a huge community model. We're now working on making that as a service available to other communities as well. What we also have, so we have real-time forcing from the weather forecast. As I said, we're now running GFS. We're switching to ECWMF, hopefully this summer. Data simulation, we have kick-ass visuals, and we have someone at eScience Center to thank for that. Because this is all modular, if you now think, well, I'm doing something different, but that style of visuals is interesting, just go to our GitHub page and just steal only that part. cite it properly, but use it. Some of the lessons that we learned in building this, especially from the fact that we're not computer scientists, HPC, especially I wasn't, Dr. Drost is that what we always thought as hydrologists to be a problem, you can't run globally because our computers are not big enough or because our problems are too big. You just start building it, and it turns out it wasn't such a big problem after all. We learned that if you build it from little Lego pieces, it clicks together really well. And we learned, I think I said that already, you should just start building and you'll see where you'll end up, but usually you can make it work. Of course, there's a whole lot of limitations and to do before we can actually use the data from this to base decisions on. We need very good validation, we need lower resolution forcing, ECWF like I said. The memory issues are an issue now. We're running 24 ensemble members, I believe. And for proper statistical uncertainty predictions, you want to go 100 at least. This is also something that the weather services do. They're running 24 ensemble members because of computer size, not because the statistics say that 24 is good enough. The time steps need to be smaller. There's a whole lot of stuff. One of the most important things that human interactions need to be modeled into there. So we're setting up a project where we want to look at, we're predicting reservoir inflow for hydropower, and then hydropower companies are giving us their scheduled management decision that we then use iterative for whatever's happening downstream. A lot still to do. Continued funding is of course there as well. This was fun to build. I'd like to emphasize that as well. We really enjoyed making eWaterCycle. We think it can have an impact, but there's still a lot of mainly computer issues to solve before we're there. Thank you for your time.